Hello. Let's wrap up our discussion about binomial distribution, and let's sort of look at the last little bit of this where we can maybe take a picture of some sort and turn this into something close to a histogram. Remember the binomial distribution. It was a process whereby we could sort things into pass or fail, success or loss, and we could discuss this formula for it. For a precise number, r successes out of a fixed number of n trials. As we've gone so far in statistics, we've seen some interesting formula calculations for population deviation. The first one involved a list of numbers. X minus mu quantity squared, each of those summed up, divided by capital N. You take the square root and you find the population standard deviation. As you found this population standard deviation, you had clearly in your mind that you had a list X and it had a whole bunch of raw data scores. You could add them all up, divide by capital N, find mu, and then from there you could calculate the normal amount of data turbulence, variance, and take the square root of that and get standard deviation. However, a couple sections ago, we finally developed the ability to talk about probability distributions, and suddenly our data changes. It's not a long list of raw numbers, it is in fact a list of certain events, maybe our CEO is turning certain ages, and a probability of success for each of those events. It's not necessarily that this list is shorter, it's just that it's a system where we know more information, because the fact is that we have a great deal of data when we have a probability distribution contained. We're going to pause for just a second as I change out the video battery, and then I'll be right back. And we're back. So with this probability distribution, it's not that we had shorter numbers. It's just that we had more data about the system. And if we know that we have not just any binomial probability, not just any, probability distribution, but in fact a binomial one where there's only two possible outcomes, then we know even more, and we can in fact sort ourselves into a scenario where standard deviation is just the number of trials times the chance of success times the chance of failure. So, let's take a look at an example that's near and dear to my heart, and probably yours as well. Seconds ago, I had looked in all of my student data for the last couple of years, and I had grabbed a little over 200 students just in statistics, and I sorted that data into win or lose. In particular, every student in my class earns a grade of some sort. You can either earn an A, B, or C, depending on if you usually perform above 70% in all your categories. Or there's students who earn under an A, B, and C. And D very well may be a passing grade. I've heard the phrase D's get degrees, but usually for transfer purposes, and oftentimes, of course, for progressing to the next class, a D isn't quite the ideal grade. So, as a professor, I often look at these numbers. I look at my ABC rate, which again in the last couple of years in statistics has been about 0.53, and I look at the complement of that. These are all the students who earn a D, an F, maybe they got sick, maybe their parents got sick so they withdrew, they quit the course because they got a new job and had to move somewhere else. All sorts of things happen to students in this other category, but perhaps we can call it ABC complement, and of course 1 minus 0.53 leaves me with 0.47. So now I have sorted things that seemed to be qualitative, and in fact seem to be rather more than just one or the other, because we have A or B or C or D or F or W or some sort of Q or withdrawal. But in fact we can sort this into success or not success if we like, and get these sorts of numbers. If we do this, we might be interested in calculating a couple of probabilities. First of all, what's the chance that I have no students succeed? Remember, for binomial distribution, we have to commit to the number of students. You have a fixed number of trials. In the last example with students I did, we had successfully talked about 33 students. But 33 is quite a few things to fit on this board, and so I'm going to think about a slightly smaller class that I've had. We only have 17. It's just a bit smaller, but it's still very real. What do I expect as I walk into this 17-person class for the first time? Well, I can expect all sorts of things. What's the chance that I have no student pass that class? For any one student, it's a 47% chance that they will not earn a passing grade in the course. So for the whole class, how does that change? Well, we're calculating a probability distribution. Notice this time, my definition of success is in line with what I would call the normal definition of success. Namely, if I'm successful in the class with an ABC rate, that would mean that that student has successfully passed the class. We're not doing this weird opposite world where success is somebody dying or success is someone having flu virus, maybe like we discussed last time. So what's the chance of no students earning a passing grade in the course? Well, we have to commit to our 17 trials. We know our probability of success is 0.53. And that means 1 minus 0.53 gives me 0.47, and that's our probability of not success. Remember, the binomial distribution gives me exactly 0 people, so if I want no students to pass the course, then we would be calculating probability of 0. Ideally then, 1 minus this will give me the chance that at least 1 student. So we calculate this out. Maybe using our combination formula, we have 17. Choose 0. And then we have a probability of success being 0.53. And we raise that to 0. Because we're curious, what's the chance that no student earns a passing grade in the course? Times 0.47 raised to the 17. We know plugging into our calculator that anything choose 0 is going to be 1. Anything raised to the 0 is 1. Well, any constant number at least. So all we really have to plug in is 0.47 raised to the 17. So I pop in 0.47 exponent 17 and hit enter. And we get ourselves 0.1234527. This is the chance of no student earning a passing grade in the course, and it seems quite small. While there may be a 47% chance for any individual student to not earn a passing grade, once we get a group of them in a cluster, we're pretty certain that at least one will. In fact, if I want at least 1 student to earn a passing grade in the course, I would do 1 minus p of 0, which would be 1 minus this, and that would be 0.99 stuff. I'm almost entirely certain that at least 1 student will earn a passing grade in the course, and that's probably a good thing. But we're not interested in just 1 student. That's the student view. That's where you're concerned, of course, but I'm interested in total class size. And of course individuals, but total class size. What do I expect when I have 17 people in the room? How many people do I expect to see earning an ABC? Well, that's called expected value. That's called mu. Mu equals 17 times 0.53. And if I do that multiplication, then I get myself 9. 9.01 in fact, but we'll round up since it's whole people. I can also calculate my standard deviation. That will tell me how much turbulence I expect, how much variation away from 9 of these 17 are we expecting. 17 times 0.53 times 0.47, all under the square root. So I can hit second in the square root formula, and then I can hit 17 times 0.53 times 0.47, and I don't need to use any parens. And I'll get myself approximately 2.1. Well, now we can start to look at the normal distribution for this. And this leads the way to what we're going to discuss in the next section, namely the normal distribution. But already, remembering from our histogram charts that we called normal, when we first drew those, we had this idea that the highest number that was happening in the middle would be the most likely thing to occur. And then as we spread ourselves out on either side, we started getting different standard deviations. Let's go ahead and actually round this to whole numbers so that this is easier to calculate, just for this example. If I round this to 2, I could have 9 plus 2 and get 11. And I could have 11 plus 2 and get 13. We call this mu, we call this mu plus sigma, and we call this mu plus 2 sigma. If we go on the left, I have 9 minus 2 is 7, and I have 7 minus 2, which is 5, and this again would be mu minus 2 sigma, mu minus sigma. And this is very interesting because we had Chebyshev's theorem, which promised us that at least 75% of the students would fall between two standard deviations. That's because Chebyshev said something like this is a minimum. And so if I plug in 2, I get 1 minus 1/4, which equals 0.75. And I in fact said later on that we will actually talk about a rule that for normal data will behave better, and we would expect students to behave normally. Chebyshev doesn't tell us at most, it tells us at least. What does this mean? It means that at least 75% of the time, if I walk into a classroom of 17 people at the start of term, I am expecting between 5 and 13 of those students to earn an ABC. It means that if I have only 4 students earning an ABC, I start to wonder to myself, what was different about this semester? And then I look back and realize that we had an instance of the Black Plague go through, and that all the students who didn't pass were in fact dying, and it was very sad. On the other hand, if I have 16 students earning a passing grade in the course, I start to wonder to myself, what was vastly different this time around? And then I realized that that semester was the semester that we, grabbed all the calculus students and gave them iTunes gift cards if they came to that particular stats class. And so we had something very different than usual. But in general, I expect between 5 and 13 to earn a passing grade. And in fact, that's pretty usual across the course. I don't normally see breakout performance, either good or bad, on a final exam. So throughout the entire term, I'm keeping in my mind 5 to 13. And anytime I see a midterm or some sort of quiz grade go over or above that, I start to wonder, was that quiz too simple? Did I not discuss it properly? If it was under, what happened? Why are students not performing as I expected? In fact, this is an area of science that's often called control charts, and you see it all the time in business. If you start running factory productions and you're curious how likely were different products to be needing to be sent back for repair, how often do toasters get their warranties used? This is all about controlling things and saying, mostly we expect them to behave in this range. When they start to behave outside that range, things get strange. But what I really want to do is draw a photo. I've drawn a sort of little one right here, but I'd like to draw a better one, and since I'm not a great artist, I think that technology can probably do that for me. So let's see if we can pull this off. At the moment, there's just a whiteboard here. But now let's pretend that I snapped my fingers, and that wasn't a very good snap, so let's try it again. And now you can see that there is actually something here, and it's quite interesting. I've had Excel draw this up. And what you can see is down here on the x-axis, there are interesting divisions, and those divisions are whole numbers, and those whole numbers are numbers of students. At the far left, you see 0 for the probability of 0 students earning an ABC in the course, and at the far right, you see 17. And on the y-axis, we've drawn out those probabilities of success, where I've had the computer program Excel calculate P of 0, P of 1, P of 2, P of 3, all the way up to P of 17. And as you can see, this is drawing itself in a normal distribution. It's a normal mound shape. It's behaving symmetrically. It's being very nice. And right here in the middle, where we have the highest chance of this something happening, you're seeing those calculations we saw before, namely that we expect somewhere around 9 to be usual, and then we have the standard deviation of plus or minus 2, roughly, in either direction. This is where it usually happens. And then we have these extreme cases here that are very unlikely to occur, which is why they're not so high up on the y-axis. This is a probability distribution chart. So let me talk a little bit about how I got it. To do that, let's send this chart back, and then let's take a look at the formulas that we used in Excel. And of course, I do have another video with an Excel program that maybe runs through the mechanics of this, but just let's talk. In Excel, we tend to write equals a lot whenever we want to call in a formula. So what I did in Excel is I set up 2 columns. I wanted the binomial distribution equation, And then in another chart, I wanted to talk about the number of people who were going to earn a passing grade in the course. So I coded in 1, and 2, and 3, and 4, all the way down to 17. So I filled up that one chart. But to the side of this, I wanted to do a formula. I did this in the B column. This was row 1, and row 2, and row 3, etc. What I did is I coded in a formula here. And so this very first term right here would be B1. That's the cell that zeroes in. The second one would be in column B and row 2, column B and row 3, and so on down the list. So that's what I mean when I'm about to write these B's. I think my eraser here is not going well, so let's try to get rid of it. Then over in this binomial distribution column, we code up this equation. In Excel, if you start to type in equals and start to type in binom, I think it's binom.dist, but by the time you got to NOM, it will be trying to autocomplete it for you with the correct one, so then just double-click that. And then it will give you a parens, and then it will start telling you the different pieces of information it wants from you. And those pieces of information it wants is going to be your number of successes that you're after. It's going to want to know your total number of people that you've got in there. It's going to want to know the probability of success. And lastly, it's going to ask you whether you want it to be cumulative or not. And that's going to be a true or false command. So if I remember my order correctly, what you start typing in is you type in R, the number of successes you're after, and you don't type in R. Instead, you're going to type in B1, and that will grab the number 0. You also are going to need to code in the total number of trials. Remember, we need to know how many trials overall we had. In our case, this was 17. Then you're going to code in your success chance. That's 0.53. And Excel's clever enough that it will automatically do 1 minus 0.47, so it doesn't need to know that. I may have mixed up the order of these three things, but you can work it out. They're going to use different letters than they would use in this set of things that I've done. So I've used P, and then I've also used R, and I think they talk about S success rates in Excel. But you can play around with the problem when you know the actual calculation. Maybe go back to that P of 0 one we just did, where you know it was 0.050 zeros and 26, and make sure that you're coding it into Excel correctly. What I really want to talk to you about is this very last piece. You can either type in true or false. And for everything that I've been doing so far, what you want to type in for Excel is false. That will tell it that you just want exactly 0 successes. Excel makes it very easy to calculate something like at least 15 successes, or at most 15 successes. So, we can look at this binomial distribution, we can look at our chart, and this pretty much wraps up what we do with binomial distribution. There is a little bit that you can do that talks about how many you want to have in your sample size. So look at the example in your textbook that discusses that quota problem. Maybe quota has an O. The book that we have usually suggests looking it up in a table. Of course, with Excel, you can auto-generate these percents. Either way, your idea is, if you want a certain minimal level of success, then you have to figure out, well, I need to have how many students to achieve this. So let's say that I knew that I wanted to have at least 20 students earn a passing ABC grade in my class because I needed to have 20 people to do an after-class survey on. Well, then I would start seeing how many students would I have to invite to guarantee myself that I probably had at least 20 of them successfully earn a passing grade. We already know that for 17 students, I'm expecting about 9. So if I want 20, how many more do I have to have than 17? I'd obviously need at least 20, but having all of them perfectly earn ABC rates is probably unlikely. That pretty much wraps up this section. In fact, it wraps up this module. So where do we go from here? Well, first of all, let me rewind that. Let me once again encourage you that ABC rate is entirely up to individual students. What do I mean by that? I, of course, expect 9 people out of 17 perhaps to earn a passing grade. And I might expect between 5 and 13 out of 17 in general. But the odds are in your personal favor. You have a better than half chance of earning a passing grade. And let me tell you something about this 47%. It's not quite as grim as it looks. Because the fact is that lots of students actually drop the class for no reason to do with grades, but for other things. You get sick and go for an extended 3-week stay in the hospital. Well, there only are 16 weeks in the course, so 3 out of 16 missed content naturally is a big issue. Parents get sick. Grandparents get ill. And this sounds like a whole cornucopia of terrible death and dying. That sounds sad, but what I'm saying is there's a great deal of life that happens today. And in general, the median student has 2 kids, works a couple jobs, and is responsible for various family members. It is no real problem if life happens and you suddenly have to withdraw on a course. It happens. It's usual. It's expected. Remember earlier on we said that 20% of students don't engage in the homework? That number was in students who I counted for actively still in the course. You can definitely improve your odds to push yourself into this category by doing the homework. In fact, if you're curious by the numbers, here's the behaviors you should avoid if you'd like to get yourself into that 0.53 area. Let me erase that quote of business. So I can end this section maybe talking about how do you beat the odds. Do your homework. That seems obvious, but it's one of the biggest sorters into these 2 categories. 20% of students don't do their homework, and 100% of those 20% find themselves in the 0.47. It is conceivably possible to earn a passing grade in the course without doing your homework, and please don't take this as a challenge, but the fact is that it never happens. Ever. I have never seen it. After teaching almost 3,000 students, I have never once seen someone not do their homework and pass the course. Could they by the percents? Yes. It's unlikely. And why risk it? As part of this do your homework process, visit my office. Does it happen that a student who steps foot into my office earns a not ABC rate? It does. But the majority of students, particularly those who show up to my office before the first 5 weeks are up to discuss study strategies, something like 87% of those find themselves in this category. You get out of a class what you put into it, as always. If you come up to my office, you're likely to be asking questions. You're engaged. You're working the homework, you're reading the book, you've got questions to ask me, and therefore you're going to be doing all the right sorts of behaviors that do predict success. I find my office is scary, and I do want to promise my students that I have this nifty little bowl here, and inside of it generally is candy. I think a math professor's office is possibly the scariest place on campus, and I'm told that I'm more frightening than getting flu jabs. So I think maybe the candy makes that better. So come to my office, visit my office, get some free candy, and ask some questions. What's another thing that I think doesn't happen? It's possible in this day and age, when I release my quizzes digitally, that I can look at not only when the students took the quizzes, but whether they went back into the quizzes afterwards and tried to revise and develop a sense of understanding. And students who earn a passing ABC rate in a course almost always go into their quizzes after it's done and they look at them. They look at the correct answers, and they spend more than just a few seconds in there. Now, my tracking technology isn't perfect, but it's pretty good. And so I can say that generally 4 to 5 minutes at least per question that was not answered correctly on the quiz is spent inside the quiz place. And I assume they take that information then and go out into the world and use it and practice it again. But this idea of going back and doing that deliberate practice, doing your homework, and going back and deliberately practicing on things that didn't work, I would say, is probably the two biggest things you could do to change this. And in fact, if every student did those, I would have to revise these numbers, and I wouldn't be surprised if 15 or 16 out of 17 earned passing grades in the class. The truth is that probably sickness and personal reasons that require withdrawing from the course only account for about half of this. The rest I would put down to engaged, fully engaged student behavior. So, we've looked at binomial distribution, we've taken a look at a picture. With any luck, I have wowed you with my technical wizardry. And where are we going to go from here? Well, as we had seen a second ago, right here, and perhaps we can think about that, that overall graph shape that we had was normal. And we had said with Chebyshev's theorem, if we go 2 standard deviations in either direction, we can expect ourselves to have at least 75% of everyone living there. And so I say, well, between 5 and 13 people out of 17 student class. We want to take this further. What if I don't look at just some numbers of students, but what if I look at things like height, random variables that are not so much discrete head counts as continuous, measured height inches? How tall am I compared to the rest of the world? How tall am I compared to the rest of the United States? How does me personally, as an individual data value, compare to the population as a whole? That's something that we're starting to get here. Individuals, 0.53 or 0.47. The class as a whole, 9 people approximately. My coworkers are staring at me strangely, and I admit I am talking to myself. So as we do this, we're pushing forward into the next section, and we're having this idea that most likely, we should be able to talk about continuous variables, and we should be able to compare individuals to population behavior. And that will be pretty exciting. But until I see you there, keep on revising, keep on doing your homework, come visit me in my office, and be safe.